Good morning, everyone. I'm sorry that I could not be there for class today, but we're going to go through our lesson for solving trigonometric equations. Basically, it's going to follow the same path we talked about before solving any type of equation. However, there will be some interesting twists along the way because of the fact that trigonometric equations give us infinitely many solutions all of the time if we're looking at a domain that's wide enough. Two things to keep in mind. When you're solving a trigonometric equation, you're going to see both theta as your variable and x as your variable. If it's theta or any other Greek letter, we're going to assume that we're in degrees. If it's x or any other Latin letter, we're going to assume that we're working in radians. So our first example, we're going to solve the equation 2 sine theta plus 1 equals 0, and we're going to restrict ourselves to the half open interval, including 0 degrees up to but not including 360 degrees. In a sense, one revolution around clockwise or counterclockwise. First steps are going to be pretty obvious. We need to get sine theta alone. So we're going to subtract 1 from each side and divide both sides by 2. Once we get to this point, we have sine theta equals negative 1/2. We're now going to consider quadrants of our solution and a reference angle to our solution. We work with them independently. The negative on the 1/2 is going to help us with our quadrants. If it were positive, it would also help us with our quadrants. The 1/2 itself is going to get us a reference angle that we can apply to our two quadrants that we choose. In this case, we know that since sine is negative, theta must be a quadrant 3 angle or a quadrant 4 angle. That's where sine is negative. And then as for finding the reference angle, we don't care about the negative. We're more interested in when sine of theta is 1/2. What first quadrant angle, what acute angle sine of theta is 1/2. So we're looking for theta prime, our reference angle. It will be arc sine of 1/2. And you should all know at this point that arc sine of 1/2 is 30 degrees. So that means we're looking for third and fourth quadrant angles that have a 30-degree reference angle. So here we go. In quadrant 3, 30 degrees away from the x-axis would be at 210 degrees. In quadrant 4, 30 degrees away from the x-axis would be 330 degrees. And there it is. We have our two solutions that are in the interval from 0 to 360 degrees. Much of the time, though, we're not going to restrict ourselves to this interval for solutions. Instead, most of the time, we're going to be interested in finding all of our solutions. But the process is going to start exactly as it did for this and get us to this point, because this point then helps us find all of the solutions. So these are the two solutions in the given interval. Example 2, same equation, but now we're going to look for all solutions. So the first steps are find those baseline solutions, which we did. They were the 210 degree and 330 degree direction. All solutions to this equation must be in the same direction. That is, we need to find all angles coterminal to 210 degrees and 330 degrees. We have seen this one time in the past, so I don't expect you to remember it, but it's just a matter of taking that baseline solution and adding on every possible coterminal angle. So we always get our coterminal angles by adding any integer multiple of 360 degrees to that baseline solution. For quadrant 3, which was a 210 degree angle, our solution in that direction would be theta equals 210 degrees plus 360 degrees K, where K is any integer. Our quadrant 4 solution, theta equals 330 degrees, becomes theta equals 330 degrees plus 360 degrees K, where K is any integer. And that's what you will need to do on your baseline solutions to get all solutions. Just add on the 360 degrees times K, where K is any integer. In our next example, we're going to solve this equation. Sine theta tangent theta equals sine theta, and we'll do it for all solutions. It begins by finding all the solutions from 0 degrees to 360 degrees, and then adding on the coterminal angles for that. In this case, it will be helpful to solve this equation for 0. That is, subtract sine theta from both sides and factor the result. After we subtract sine theta from both sides, we get sine theta tangent theta minus sine theta equals 0. You'll notice that sine theta is a factor to both terms, here and here, and so we can factor that out. Sine theta times quantity tangent theta minus 1 equals 0. Once you have it set equal to 0 and factored, you can set each factor equal to 0 individually by using the zero product property. So that sine theta equals 0 or tangent theta minus 1 equals 0, which would mean tangent theta equals 1. We now have two paths to our solutions. Sine theta equals 0, tangent theta equals 1. For sine theta equals 0, that happens twice. It happens at 0 degrees. I'm so sorry, I missed my degree symbol here. I know you must all be happy that I made that mistake that I'm always catching you on. So for all solutions, that would be theta equals 0 degrees plus 360 degrees K, where K is any integer. Yes, you could have just written theta equals 360 degrees K. It means the same thing. But sine theta equals 0 also occurs when theta is 180 degrees. So that means 180 degrees plus 360 degrees K, where K is any integer. This would be the first half of our solutions for sine theta equals 0. Now for tangent theta equals 1, since tangent's positive, that must mean a first quadrant or third quadrant angle, and our reference angle would have to be 45 degrees. In the first quadrant, our solution would just be 45 degrees plus all the angles coterminal to that. In quadrant 3, 45 degrees away from the x-axis would be 225 degrees, and then all of its coterminals. So we have four sets of solutions, 4 different directions. 0 degrees plus its coterminals, 180 degrees plus its coterminals, 45 degrees plus its coterminals, 225 degrees plus its coterminals, and yes, you do need to have where K is any integer every single time. Our next example, solving tangent squared x plus tangent x minus 2 equals 0. You'll notice that there's something important about our variable here. Can you figure it out? So what's important about our variable is that it's a Latin letter, so we're now working in radians. Make sure that you are paying attention to the radian values and not just degree values. So we're starting with this equation, which it's quadratic. Tangent squared x, tangent x, constant. With it being quadratic, we can factor it. We need to find two numbers that add up to 1 because of the 1 times tangent x, and two numbers that multiply to negative 2. Those two numbers would be negative 1 and positive 2. So our two factors would be tangent x minus 1 and tangent x plus 2. And once again, by the zero product property, we can set each factor equal to 0, so that tangent of x would equal 1, or tangent of x would equal -2. We've already done tangent x equals 1 in the previous example, but we did it in degrees, not radians. So we'll just use the radian equivalents. So first and third quadrant, our reference angle x prime is going to be arctangent of 1, which would be pi over 4. In quadrant 1, pi over 4 plus 2k pi, where k is any integer. Remember that in radians, each revolution is 2k, each revolution is 2 pi, not 360 degrees. For quadrant 3, pi over 4 radians from pi radians would be 5 pi over 4 plus 2 pi k, where once again k is any integer. Now, for the option of x equals -2, this is not one of our exact values. We do know that because tangent's negative, we're looking for solutions in quadrants 2 and 4. Since it's not going to be able to get an exact answer, we will approximate this using our calculator. The calculator will need to be in radian mode for this because we're using x as our variable. If it were theta, you'd have your calculator in degree mode. We start by approximating the reference angle x prime using arctangent of 2, not -2. When we're looking for reference angles, it's always a positive value. And our reference angle would be approximately 1.1071. We would now need to get our two solutions in quadrants 2 and 4. For quadrant 2, we'd have to go backwards 1.1071 radians from pi radians. This number here, 2.0344, is pi minus the reference angle. So 2.0344 plus 2 pi k, where k is any integer, would be that solution. For quadrant 4, we get by going a full revolution to 2 pi radians and then coming back on our reference angle. So 2 pi minus 1.1071 is the 5.1760. Add on 2 pi k. There should be a k here. I don't know if I can draw that in. I guess I can't. Thought I could. Let's go back. All right, so should be a k here, 2 pi k, where once again k is any integer. So once again, in this case, we had 4 solutions. We had 0 radians. No, we didn't. We had pi over 4 radians, 5 pi over 4 radians, 2.0344 radians, 5.1760 radians, and then plus 2 pi k, where k is any integer, on every one of those. All right, so that's all you need to solve trigonometric equations today. If you noticed in your outline for Unit 7, we actually have 2 sections for solving trigonometric equations. And the other one was scheduled to come next. We're doing Chapter 6, Section 2 today. And originally I had scheduled Section 3 for tomorrow. But then I remembered that we actually need a lot of stuff from Chapter 5 before we can do Section 3. So the order that's in the outline is going to be different than the order that we will cover it after today. We'll talk about that new order tomorrow and get started in with the stuff from Chapter 5. Have a great day. I will be around later today if you've got questions, or you can shoot me a quick email, or we can talk about it at the beginning of class tomorrow. Have a great day. Thank you very much.